Yes. Hello, dear colleagues. My name is Mikhail Vasilyev. My presentation today is about searching of anomalies in Python. Traditional slide about myself. I am senior specialist in machine learning in the MacBoss. We are doing corporate security, and I'm solving tasks of computer vision, processing of natural language, and search for anomalies, and I'm going to be speaking about it. Also, I'm contributing into the open source if I have possibility for that. So let's begin. Anomaly search. It's a subset of data science. It's a very interesting subset, but it seems that not much attention is paid to it. And at least in the RuNet, I've discovered not enough materials where people would speak how it has to be properly cooked. So I decided to make a presentation like that. I think that this is a back-end audience, at least it seems to me. There are data scientists who can leave their hands, at least we have few. Good. Okay, I will speak to backenders and I will chew it up to small pieces and dissect it for you. But I will make references to classical ML so that data scientists would also have something to catch on to. So, anomaly search. Anomalies are data records which are so different from other normal records, so that it seems as if they were born by some other distribution. It's not really understandable definition, so let's give a more specific example that I really like myself. On Random Coffee, I've been communicating with a colleague. She works in online gaming industry, not casino, but online games. Her task is to discover and ban, with the help of ML, bad players, those who write bots in Python so that it would collect loot for them, play for them, etc. Or the players which use bugs in the game to get certain advantages and collect a lot of loot. Or maybe some unclear players, unknown players who somehow have accumulated a lot of score, definitely dishonestly, but you have to figure out how they did it. So my colleague, she finds them and bans them because they are reducing the pleasure from the game for good quality players. So her job consists of two stages. Stage number one, take the data, find examples of those bots, put them on the board, and train some machine learning models so that in the future it would work and work all these petabytes of data. Well, it seems everything's okay. But there's a peculiarity. As soon as she rolls up this model, binary classification, basically, well, data scientists, hello, an interesting thing begins. Bots, they are being rewritten. And then the fight begins. The bot was clicking once per second on the screen. Okay, it will click with some noise, not once per second. And it's much more difficult to find them. And if you want to find accounts like that, it's much more difficult with every iteration. And you want to automate something. And you want to automate this data collection part, because it's not really understanding how to find them. You need some accounts which are really different from other accounts. And what it is, how can you formalize it? Nobody knows. And one of the ways to formalize it, it's, okay, let's see. I have a certain synthetic data from two signs measured in snakes and parrots. Squares with data. At the bottom on the right, you see the cluster, very dense cluster of normal data, and it's surrounded by some anomalies that we'd like to discover. A beautiful solution would be to invent some anomaly index where every data record will have some number, which if it is big, it's going to be anomaly. If it's a small one, it's a normal data. We don't know how it's going to be happening, but it's wonderful. We have to sort it, take it, and take top 10, top 100, top 1,000 records on this index of anomaly, and then we should analyze it, and it's going to be much simpler. Or we can do the following. We can build a histogram of these anomaly indexes. We can select some threshold value, after which we can say, okay, if it's going to be more than this threshold value, it's going to be an anomaly. So in my synthetical calculations, I've done it like that. I knew, because it's synthetics, I knew that it's going to be 20% of anomalies. I've selected this threshold value. And look how beautifully all anomaly data was cut away. In reality, it will never be like that. But still, this is a pretty cool result, but nobody knows how to get it. Okay, I would like to tell you a couple of words about practical applications so that you would understand that it's not only about online games, it's also about banks, where it would be good to search for fraud and criminals. It's to provide cyber security, because I'm working in this sphere. It's easy to search corporate spies, hackers, and others. Let's dive into the problem, and then we will go to interesting algorithms. I will tell you that I will search for anomalies in table data. Doesn't matter which kind of tables, Excel tables, SQL tables, just search. And search of anomalies you can also do in numerical lines, in text, in pictures, graphs, everywhere. And I'm speaking just about the tables, base, and methods out of the table data are easily transferred to other domains. So I would like to give you 3 properties of anomalies. Anomalies are very seldom. Well, by definition. Second one, anomalies are very diverse. Bot holders, people using bugs, players that using different mechanisms, different types of anomalies, but nevertheless, they all have to be found. And then anomalies are evolving, they are variable, and as we've searched about the online games, if we cooperate with them, they're changing, and it complicates the objective. Complicates the task. The task of anomaly search can be divided by different ways. The most popular one is training without a trainer. When you get certain data, you know that this data has anomalies, and you have to find them. It's a very good objective. Go, you don't know where, find, you don't know what. But people find it. The second type of tasks, learning with a teacher. For data scientists, well, they know it. You have data. In this data, you have a certain setting. For example, in a certain column, every anomaly has one, normal data says 0. And classical data science solves this problem, but it's not as popular because, first of all, it's not a fact that you have all types of anomalies in your markup, and it's not a fact that after you will search your beautiful data science classifier, anomalies will not change, and its value is not going to drop. And the third type of objectives, I don't even know how to call it in Russian, it's semi-supervised learning. This is when it's interesting, the data is delivered to you, also not marked up, but you somehow know that in this data, either there are no anomalies or anomalies are very small. And we are going to learn how to work with these. This is also a pretty cool moment. And we'll speak about what kind of anomalies exist. The simplest one, even though, well, it's called global anomaly. This is when some signs in data take some seldom values, very big or very small or very rare. Well, it's very easy to search for them. For example, in this graph, you can see an example. Yellow points is a global anomaly. Sometimes we have a context anomalies. They are tricky. All signs have normal values, which regularly are not different from regular data, but the combination of these signs is unusual. My great example is Moscow's weather, 29 degrees. Well, it's a normal weather. It happens in Moscow like that. But if you observe it in November, then it's an anomaly. An anomaly combination of signs. And collective anomalies, well, everybody knows this. It's DDoS. When every request separately, it's not an anomaly, but the fact that collectively they came at the same time or very close time-wise, it creates a collective anomaly. Today, we are not going to look at them because there are separate methods for that, and we are getting closer to an interesting part, where I'm going to tell you about algorithms, but first of all, how can I call it? A warning. sometimes anomaly search can be solved very easily. For example, you know from empirics and communication with experts that you will observe the only type of anomalies when the temperature from the sensor is above 50 centigrades. This is also an anomaly. Temperature has grown, but you know that only such anomalies exist for us. Or, for example, you can apply some normal distribution to your data, and you can say, okay, I'm coming from the preposition that my data is distributed against some median value equally. So the difference from this median value is the index of anomaly. If something is too far away from the median, it's anomaly. If it's close to median, it's normal. If in your task you can apply one of these simple empirical knowledge, apply it and don't be too smart. This is my disclaimer, and right now let's go to the interesting part. How in Python we can realize this complicated objective when you have to, not marked up data, determine their index of anomaly. That's how. 4 lines. Because this is Python. Everything is solved in 4 lines. You, in data variable, by array from your in variable scores, you record anomaly index. The only question that you might have, what is this iForest method that we are using here? If other methods, and how is this method applicable to us? Spoiler, there's a lot of methods like that. For example, in PyOD library, which is very central one for the Python for search of anomalies, they have realized approximately 50 different methods. They are various. They have strengths and weaknesses. And today, I would like to make a presentation and tell you about different classes of algorithms so that you would have a general understanding of what is available, what can be used, and let's see how can it easily be attached to anything. This is wonderful, and it can easily work in your startup or sub-project. Classes of methods, I will have some linguistic setbacks so that humanitarian people would feel pretty good because I'm a humanitarian person. If you've been reading Canterburyan stories, you can lift your hands or give me applause. Somebody read it.
A man is known by the
Okay. He keeps, it's an epigraph to the methods based on proximity. Okay, this is our data graph, which I've been using today, and we've been saying that we have a cluster of normal data. Around it, it's surrounded by noise and anomalies. And the first idea that comes to my head, okay, let's see. Normal data are in close proximity and anomaly is too far away. Okay, let's use it. Let's see, we take a random point. Around it, I make a circle and increase the radius of this point. But honestly, the distance from this point in the center to the neighboring point, close neighboring point, can be some index of anomality. If it's a big distance, it's anomaly. If it's close, it's normal data. Logical. But the only situation when it's not going to work, okay, let's see. Somewhere on the left, we have some cluster of anomalies in such a way that they are very close to each other, and this approach is not going to work with them because they will give very small values, and we will take them for normal data. It can be solved very easily. We take not closest point, but 10th, 15th, and 20th. And number 5, the distance is very good and big, and the point is shown as anomaly. Data scientists already have recorded its K closest neighbors method, but adapted for search of anomalies. And I have shown the graph, K nearest neighbors, K equals 10. I've marked up all my data. I put it in the algorithm and shown it in a graph. The more yellowish they are, the more anomaly, the more pinkish, the more normal they are. It works. Plus of this method is that it's a very simple method. I have a nephew, Sasha, 10 years old. She can do it in her better than Pythonist. But the disadvantage of this method, some people feel, those who've been solving projects and lead code, complexity of square point. For every point, we have to calculate distance to all other points. We repeat it for all other squares in a square. In the Python, realization is much faster. It's optimized, but nevertheless, disadvantage is that it's very slow. Okay, let's move on. Fault sera, se faire petit farrois. Those who know French, you can wave your hands. Somebody knows French? Okay. This is a quote from Joe Dassin. Sometimes you should know how to be small. And it's an epigraph to probabilistic methods. Everything is very simple here. Okay, let's see. For example, we have data about certain company and its employees. For example, we know that 4 signs of these employees, age, salary, premium, bonuses, and we would like to understand that certain employee, 30 years old, with a salary 50,000, bonus 15,000, and 5th grade, how anomaly he is or not. Okay, we can begin with a simple thing. Okay, let's put him on a graph. Here he is. Here's the guy. And there is a very simple idea that, okay, let's say, if the column where we find this employee is very small and it's anomaly. If it's very high, then it's a normal data. But one thing that we'd like to find, we'd like to unite all these 4 signs. So we have to combine them and find a median so that we don't compare and don't add up apples with oranges. Okay, let's normalize this data. For example, let's see, we say that age has 1 employee, salary 29, etc. And for example, we divide it by the height of the tallest column in the histogram. For the first one, the tallest one is 100. Age category 20 to 25, we divide it by 100. What's next? We just calculate the median. It's almost the index of anomaly, except for the fact that we want for anomaly data it has to be high and for regular low. Okay, let's divide 1 by this number. Equal. Good, it works. So right now we have looked at a very simple histogram-based outlined core. It has an empirical cumulative reduction method. They have wonderful property. They're very fast. What should be calculated? Easy. Histogram, just a few seconds. There's another cool property, unexplainable one. We can explain why we calculate this employee as anomaly because his age is not typical and bonus is a very seldom bonus. An explanation in ML is a very big bonus and it's inbuilt into the algorithm. What is the disadvantage? It doesn't work with context anomalies. Do you remember, we've been remembering about Moscow weather in Moscow in November, and this method will give us normal data 29th in November. Come on, it was always like that. But speaking about global anomalies, it's wonderful to work. It's fast, it's explainable. My favorite German. I don't believe that we don't have German-speaking guys. I think Inter der Meister, it's from Goethe. Master shows himself in limitations. And this is a transfer to the linear methods. Let's see. We have a certain cloud, point cloud, 3D graph. Nothing is clear. What do we have in this graph? I've been making this graph. I can't understand what's there. For example, we want to show this graph to our boss, and we have to somehow put it in 2D so that it would be easy to read. How can we do that? Okay, it's logical that we would like to keep maximal information so that we don't lose data when we're going to project it. And we have to project it to a certain 2-axis. And the first axis should be selected so that we can keep maximum data spread, maximum dispersion, and the first axis will be selected like that. Looks logical. The second axis should be perpendicular to the first one. Well, in this plane, we search for another plane, an axis that keeps along the biggest data distribution, like that. And then we can project data and see that it looks a little bit more understandable. Seems that there are 2 ellipses that penetrate into each other, and it's much more obvious. And data scientists understand me that I'm speaking of a principal component analysis method. But what's anomaly search has to do with it? Well, this plane was selected in such a way so that axes would include maximum data distribution. So normal data will be located relatively not far away from this plane, but they vary in those directions where this plane is located, but in other directions they fluctuate less. But anomalies, the biggest distribution space, it's different. They came from different distribution, from different mechanisms. And there too, this plane is different. Well, sounds very strange, but honestly, well, I've marked it up. The yellowish data, the more anomaly it is. The pinkish it is, the more normal it is. And it looks, well, it's logical. In the center, we have cluster of normal data. Around it, it's surrounded by anomalies and noise. Everything works. This method has a lot of disadvantages to it. First of all, it's not going to work if your data cannot be described by this plane. Maybe your data is distributed to a certain curve or spiral or another curvature, and then it's not going to work well. Or in your data, you have a lot of anomalies, and they will shift this axis in the direction of their dispersion, and it's not going to work. Why this method is needed if it doesn't work well with anomalies? Come on, the method of anomaly search which cannot work with anomalies, but it works in this case. In case number 3 that we've been looking together with you, when the objective is that we have normal data and we think that it doesn't have enough anomalies or not at all. It happens sometimes. For example, you purchased expensive equipment with a lot of sensors, and these sensors transfer absolutely normal data in the beginning. And you don't want to break the equipment to get anomalies. You want to have a model which will warn you when anomalies will come, and PCA works well here. Wonderful. Okay. Some people know Russian. All happy families look like each other, and some unhappy family is unhappy in its own way. This is connection to the neural network. It's a Tolstoy phrase, to neural networks, because we cannot work without neural networks. Neural networks in the search of anomalies, an autoencoder method is often applied. And it consists of 2 parts, which is called encoder and decoder. It's very complicated, but I will call them the archiver and dearchivator. They work in the following way. The input data is delivered to the archivator. It's been compressed. Neural network dearchivates it. What archivator has compressed, decompresses it. It's not really understandable what I'm speaking about. But here's an example. At the input, we have vector from 10 sets of data. The first neural network compressed it into 5 data, vector of 5 data. The second network, out of these 5 data, have restored initial vector. At least it tried. But honestly, yes, it is possible. It seems that it's strange, but archivers, they work somehow. They search for certain data templates and repetitive patterns. In my data, I have a very good repetitive pattern. First 5 numbers and second 5 numbers are interconnected by multiplication by 2. 6th record is a first multiplied by 2. 7th is a first multiplied by 2. Neural network, in this case, quickly understands that if you store first 5 elements of the vector, and the second neural network will understand that it's easy to restore. You multiply it by 2, connect it in the end, and then it works. In real data, this also, it's a little bit more complicated, but it also works. They also have some interrelations between the signs. Neural network learns to find them, learns on the normal data, compresses, restores them, and the quality of the work of this neural network can be checked simply. Restored vector, you deduct the initial vector, and then you look how different they are. Very simple. Okay, what the anomaly search has to do with it? Well, because we teach this neural network with normal data, and as soon as we get an anomaly, which, well, interrelations are different, and then we have picture like that. Well, we have received a record where 5 secondary numbers, they are not related by multiplication by 2, but by multiplication with 3, on 3. Neural network have already learned, and it doesn't know that anomaly has flied in. It compresses it into 5 numbers. The second network uncompresses it into 10 numbers, and we get a big error, because totally different data, anomaly. And this type of neural networks works pretty well. Works pretty well in the cases when you know that normal data are very few and not anomalies at all. Cool. I'm pressing the wrong buttons. Okay, Chinese. I've tried. I've been searching. It's a Chinese Qinhui, something like a saying. TC Guangyin. Anna, if you're watching me, this is my Chinese teacher. And this is a epigraph to the ensemble methods. Data scientists, you can close your ears, and backenders, I will tell you what is ensembles in data science. Ensembles in data science can be done very easily. Here's going to be an example. You take data, for example, on the left part, you have the data set, and you divide it into, for example, 9 parts or 100 parts. as many as you want. I divide it into 9 randomly. And then each one of these subsets out of 9 parts, you get some machine learning model, weak one. It can forecast something. And then we remember the principle 1 head is good, 9 heads better. And then by uniting these forecasts from these 9 networks, models, we do the averaging. We average them and we give it out. This is a very cool method. It has a lot of useful properties, and one of them we're going to look at. But right now, let's go deeper into practical application of this for anomaly search. Let's begin as it was expected. We take data, we take a piece out of this data. On the left, full data, on the right, piece of this data. We look at the piece of the data and we see that, once again, anomalies are scattered. So if randomly I will look through this graph, then from one side I will have anomalies, and on the other side, anomaly plus normal data. I'll put a line. And this can be applied. For example, like that. Easy. It's a Python code, and then I have understood that there's a little error, but nevertheless. Randomly, I select certain one of the 2 axes. Randomly, this could be balls or parrots, and we select one threshold value. 395, cut it away on the graph. Okay, let's see. On the top, we see anomaly. Cool. It seems that if we will continue, well, it makes no sense on the top, but at the bottom, we still can have some fun. If we'll continue, then very fast we'll isolate anomalies. Okay, let's continue. I've selected another axis and threshold. I'm working with the lower part. It has been divided into parts, and in them we can recursively continue. It's a recursive lead code. Everybody loves it. Let's continue. We build it, continue, build it, continue, build, and if we'll continue like that, then, by the way, on the left side, you see that these 2 blocks, they will be isolated very fast because there's one cross-section on the right, and everything is going to be isolated. But with normal data, it will be very difficult to isolate them because they're very dense, and building those separating lines, it will take forever. And in principle, it seems that this is a wonderful search method for anomaly index. The earlier you isolate a point, the more anomaly it is. The only thing that you have to formalize it. Lead code, binary trees. We build binary tree in the nodes of which we record our axis and our threshold value. If you have isolated the point, you make a list out of it. If you have not isolated recursively, you continue building this tree. Cool. The higher, the deeper in this tree you go down to isolate a point, the more normal it is. The higher you isolate it, the more anomaly it is. The index of anomaly is the depth of the tree, but okay, let's take it with a minus so that it would follow the property that big value corresponds to anomaly. That's it. Ensemble this thing, build 100 trees like that, and average their forecast. So I build a forecast on 100 trees. Looks that it's pretty good. They marked up our data. They have selected this cluster and separated anomalies out of the cool. Why do we need ensemble? Why don't we do one deep tree? But let's see. I've built a contour map of this anomaly. Alongside these lines, anomaly is a continuous, constant. We've building the contour maps in school, and you see what are nuances about this space, because we've been averaging our forecasts. Forecasts from every tree is a cut stage, cut step, where every cross section is parallel to a certain axis. But forecasts of 100 trees is a super thing which looks for global context anomalies, and practically is a cell method. If you want to start from something, it will give you good result. Isolation forest, it's wonderful. Esperanto, dansu diablosh, set and mia arbaro. It's a saying, it translates. You know, if the demons are going to dance, not in my forest. And it's a practical example. I work in Makba's company. We do the cybersecurity, and one of our products, Makfest DCAP, includes a module which is based on anomaly search. We need it for specialists in the area of IS, information security, so that among all the events which are happening in the corporate network, to find anomalies, to detect some problems. Our product collects data, then puts it in database from different platforms, Linux, Windows, clouds, etc., and then records and then shows to information security specialists, well, you have a problem here. We did have limitations, of course. First of all, we've been working only with the synthetical data because nobody shares data about their own large company. Second of all, we've been selecting fast algorithms because nobody's going to wait. And it was very important to have explainability, because just to say to the specialist that, well, do you know you have an anomaly here? It's not enough. It's good, but not enough. He needs to be explained, why do we think this record to be anomaly? It will save his time. Out of cool thing, what did we get as a result? Our database holds 10 billion events and offline anomaly reading once a day, and anomalies are calculated in a few minutes. That's pretty cool. Out of interesting part, the best work after 3 billion events. It becomes faster. We thought, why? And then we have figured out assembling 3 billion events. It's approximately 1 quarter. At the end of the quarter, anomalies happening for everybody. Everybody make reports. But after 3 billion events, quarter has passed. Then it understands that it's a normal event and then starts working pretty good. And the cool thing is that information security specialist, thanks to things like that, can catch corporate spies, hackers who are masking for users, unhappy employees who are having some negative action against the company, employees who make some stupid mistakes and violate something. They also have to be punished somehow and calm down. Well, simple application of anomaly search gave us a very good and interesting result, useful for practical application. Resume of my presentation. Okay, we have looked at different approaches. Each of these approaches has its strengths and weaknesses. However, each of these approaches can be realized in Python very easily. In 4 lines, you can put your data and look at what's going to happen. Maybe you will find black swan. Maybe you will find white swan, or some seldom event which tells you that, hey guys, we have a profit here. Let's study it. Maybe we can earn some money here. But in any case, these are very small time spendings, code spendings, and gives you big result. Try it. Try to attach it to your sub-project. Play with it. Think to attach anomaly search to your startup. People don't have time to analyze data. People collect data and store data. But anomaly search seems as a good option to, without spending so much time, quickly get some interesting information from unmarked up data dump. It's going to be pretty cool. Try it. Literature? In Russian, I haven't found a single book. I found a chapter in the book, forgot the last name, but it's very complicated. You have to read it in the end when you have learned about everything. But in English, there's a lot of books about it, and I recommend you, if you're interested, please read book number 1. It's, fire. It's 600 pages in English. Pretty cool. But it deciphers everything. If you want a lighter reading, number 4 and number 5, they are relatively fresh and more practical books with code examples, etc. And at the end, QR code for my site. First of all, it has links to my previous presentations on this topic and other topics, and you can find the code of all the graphs. I have beautiful graphs. You can look them at the GitHub. Also, there's a code with anomaly search examples, my LinkedIn. So subscribe, write, communicate, talk to me, give me stars at GitHub, and I'm ready to answer your questions. Yeah, man, this is a conference where you follow the microphone. Stand up, and here's a free microphone here on the other side. Yes, welcome. Give me some light. There's going to be some light.
Спасибо большое за доклад.
Thank you very much for your presentation. I have the following question. When our data is like numerical data, generally all algorithms understandable, many things work pretty good. But as soon as we have categorical parameters, especially with big number of different classes, and if we add to them vector of numerical values, and out of this we have to find anomalies, then many methods stop working or they become very non-effective. What could you recommend in this case? And recommendation algorithms, how would you speak about it? Would you recommend recommendational algorithms? You mean recommendations, classical recommendation algorithm? Well, in recommend algorithms, if from some point of view, if you look at them, they are very similar to anomaly search methods because we, roughly speaking, there is a user item. If they are paired with one, it's one. If not, then it's zero. And then somehow we make random sampling. We use, roughly speaking, classification method, more complicated by matrix factorization. And then it's anomaly discovery method. If we are inverting these markups, so everything that is available in this data is pointed with zeros, then we do random sampling with categorical parameters. It's not complicated. You have to think about it. And then theoretically, you can have this anomaly search algorithm. Thank you very much for your question. Pretty cool. Honestly, I have to think about it. You know, it's very difficult for me right now to give you the answer out of the blue. Answering your first question, what should we do if it's not only numerical? Well, all classical ML methods are operational. One-hot encoding, something else, you just take and use it. If you have something more complicated, something like texts, then please look in the direction of NLP1 task, anomaly search in texts. In natural languages, they also have a lot of cool things, but it seems like it's going to be a separate presentation. Thank you. Sure, thank you. Next one. Thank you for your presentation. A couple of questions I have. Have you used during anomaly search in order to transfer the task from clusterization into the classification of certain bootstrapping, synthetical generation in order to make, example with anomalies, to densify this space, to make classification more simple? Yes, we've been using synthetic data due to obvious reasons, because it's impossible to use normal data. And synthetic data, you have to be careful with synthetic data, because you can shoot your foot. So we have been inviting experts to tell us, okay, guys, look, anomalies can be this way, and especially specifically in corporate, say, security, and we've been modeling them. Well, yes, we've been doing that. Thank you very much. And the second question, how strong, how often you have to retrain the models? How much they're drifting? They're drifting a lot. Retraining is done once every day, once a day, because in 24 hours, a lot of things can change. Speaking about, it's not about drifting of data, but there's a separate analysis of anomalies in flow data when the data comes as a flow and continuously changing. And I hope that I will make a separate presentation about this, because there's also some cool ideas about it and many articles written about this topic. Okay, I will wait for this. Next one. Thank you very much for your presentation. I have the following question. Are there any universal methods on anomaly search? You said that there are different types of anomalies, but is there any universal method which you have used while you're in the course of your development? You know, absolutely universal, which with a guarantee will catch all the anomalies. It doesn't exist and it will never exist. Isolation forest. This is something you can start with, and it's a collective and global anomalies. Good approach is that you apply the method, look at its markup, apply another method, look at its markup, ask experts to evaluate, do they find different anomaly types, and then most likely we'll have to use 2-3 methods simultaneously, because, well, that's life. That's life. Yeah. And also, you've told us that you have a model. What kind of this common model? You have some ensemble from different models, or one model you use? We have ensemble out of 3 models. Installation forest, I cannot tell you about other models. Well, maybe I can, but I'm not sure. But yes, we are following this particular path. We've been looking at data, which model finds which types of anomalies, and then it was the initial point. Okay, I understand you. Thank you. Then another question. How you've been generating synthetics? How did you generate synthetical data? Maybe it's a certain algorithm. Yeah, there is algorithm. You assemble expert data in a certain area of certain field. Ensemble of 3 models. I almost died. That's our work. Thank you very much for your presentation. I have a continuation of one of the previous questions about data drifting. What should be done, and can we detect anomaly in situation when data drift constantly, randomly? Is there something more smart and effective than continuous learning of the model? There is nothing more smart or effective than continuous learning. All the algorithms that we've been looking at right now, they are based on the idea that you cannot train them once and forever, because anomalies evolve, as I've told you. However, the fact that we don't use any specific marking up, it allows us to avoid this problem that we have trained the model once, and after a certain period of time, everything stopped working gradually. Yes, periodically we train it, but this training is not so long. It doesn't require additional markup, and it's not expensive. Out of those algorithms, which are the more sustainable for these situations? Depends on data. You have to check it on your own data. I like isolation forest, but maybe it's not going for you, but I have recommended it to you. Thank you. One of those questions to which you should answer not into the microphone, but if you recommend something to public, and then people will say it's your fault. Thanks for the lecture. I'll ask you a simple question. You've been telling us about methods on a probabilistic basis and distance matrix. How do you select for different data, for different distributions, perhaps? What should be chosen, probabilistic or metric methods? I would not look at distributions, I would look at your task. What is your technical specification? How much do you need to explain the forecast of your model? How much the speed is important to you? How much is the quality important for you to catch precisely these 3 types of anomalies, and better more? The more the better. That's it. Basically speaking, relatively speaking, the situation when it's not important for you to find context anomalies, but it's important to explain them, then histogram basal file score and empirical cumulative author detection, they are beautiful for this. But for example, you don't care about the speed, but you see that you don't catch context anomalies, and you just add up K and N, and then suddenly they start catching them, everything becomes super slow. So what? You just have to look at the task and technical specification. Okay, I will be more specific. The task, multi-class classification, data, very strange. Unfortunately, there's no possibility of taking an expert who would say, okay, yeah, this is anomaly because it has something wrong with business logic. This is network request, traffic exchange. Explainability has a problem here. So this is not the most important thing here. Well, if you have multi-class classification, then perhaps you have marking up. Yeah, we have markup. And then it's a very classical data science. You can use it. Just remember that you might hit new anomalies, or maybe there could be a drift of these anomalies. But if you have markup, follow the markup, create heavy transformer or light cut boost, and look at it. Thank you. I like it. It's a basic data science. Okay, we have 3 minutes, and it's not a fact that everybody will be able to ask, but we'll try. Thank you very much for your presentation. It was very interesting. I have a brief question. Have you ever tried to help in search of anomalies use language models just because they are everywhere for LLMs? I haven't tried. I've been reading articles of people who did try, and not necessarily male people. I'm not sexist. So what happens? Out of what I've been reading, they find some obvious anomalies and the principle, okay, this value has grown significantly, it's an anomaly, cool. But it seems that it's not super useful, and you can find it just by looking at the data, investigative analysis. Out of interesting what I've been reading, you put statistics of your data, like I have this distribution with this average, with such a dispersion, with so many signs, so many data, and here is I'm looking at this algorithm, some tags, something like this algorithm is explainable, and this is like that. Can you recommend me an algorithm? And this gives you more interesting results. So you have to get down and explain. It's a very cool question. Thank you. Thank you very much for your presentation. I have the following one. How do you define the isolation force thresholds, and can you use some other models for these? Whether it's going to be optimal, and do you do anything like that? I don't really understand your question. I understand that you're asking from which thresholds we select this random number for. Yeah, exactly. From minimal to maximum database. But if it will select somewhere in the medium of the cluster out of the normal data, and it will cut it in the middle, yes, it will cut it in the middle. It's not bad. It's not a problem. First of all, look, we purposefully hid into the head of all these trees. We don't want them to be too smart. We don't give them too much data, and then we average them. And if one have been split in wrong way, nothing will happen because we're 100 of them. Well, it will divide them. Normal data will be split, but it will have to isolate it, and we'll have to build it until it will completely be isolated in some of the cases. And by simple split, you will not be able to isolate normal data. But if we don't have too many anomalies and the data is very scattered, if you don't have a lot of anomalies and data is scattered, then use something like PCA. Okay. Clear. Thank you very much. And if you don't have too much anomalies, switch off VPN, or maybe you don't know about them. Okay, who asked your questions? Lift your hands. So who will be selected for your gift, and who gets the book? I have 2 gifts, one from the company and another from Positive. So I loved one question about, my God, LLM. And one question, somebody were telling us that they have some anomalies in their network. Somebody said that they already have practical task about it. No? Yeah, this colleague. And the first one, LLM, your question. Okay, wonderful. And who gets what? The blue bag here and the book there. Or vice versa. But because you already started speaking about sexism, what would you like to have? The book or the gift? Everything's okay, take it. Yeah, 3 model. Disc. Okay, guys, go and get your Postgres and good prizes to you from the conference. Thank you very much for the presentation, for questions. You can select the book, and the gift is just a gift. Enabling IT network for adults. Expert IT network. It's going to be a stand-up. There will be a lot of networking in the closed zone, and together you have to get registered. So QR code. Hoorah! You can take any book out of those that are here. Yeah, you can take this one. Of course you can take it. Yeah, it's yours. Thank you. We have 10-minute break, and then we are going to speak about work with an expert who makes advertising for social networks.